I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on using kinematic equations. Today we're going to solve problems using the kinematic equations. What are the kinematic equations? Well, they're the first three equations you're going to find on most physics formula sheets. In AP Physics 1 and most other physics classes, they're listed in this specific order. You have the equation for final velocity first, then you have the equation for position and final velocity squared. In these equations, there's only 6 total variables. So let's look at how we're going to use these. What each of the variables represent, first off, is that x naught and x are the initial and final positions. Now don't be scared by the little subscripts. That's a subscript of 0 with x, which means the position at time 0. So the 0 is pronounced naught. Then we have Vx naught and Vx are the initial and final velocities. Again, the naught being a 0, the x representing just a single direction, meaning one-dimensional, like a number line moving back and forth, not moving two-dimensionally at all. Then after that, we have listed our acceleration, which is ax. That's the acceleration. Again, x is the one-dimensional acceleration. And then finally, we have time. That's the elapsed time during the described motion. Each of the kinematic equations is missing a variable. So if we look at the equations, the first equation is missing change in position, or just the final position, which means we can't calculate it. The second equation is missing the final velocity. And the third equation is missing time. Now, because each of these equations is missing a specific variable, what we are going to do to solve these problems is we are going to list the variables, the only 6 variables, the initial position, the final position, first, because the first equation is missing those variables. Then we're going to list the initial and final velocity, then acceleration and time. The reason we list them in this specific order is because that is the order that is missing. So positions are missing from the first equation, velocity from the second, and time from the third. And then what we're going to do is we're going to put dashes in front of each of the variables that are missing from a specific equation. Let's look at an example problem. So we have an example of a car exiting the highway, traveling about 65 miles per hour, slows to a stop in 5 seconds. And what we want to know is the acceleration of the car during the period while it was slowing down. What we do first is we're going to list the variables in that specific order that I showed you. And there's a reason for that. It helps us figure out an equation. So we put the dashes in front as well of the missing variables. And what we're going to do is we're going to read through the problem. We're going to highlight, underline, whatever you can do to help us figure out what we know. So 30 meters per second, that's when we're exiting the highway. So that's the beginning of the problem. So that's going to be our initial velocity. The next is it comes to a stop. Well, if something comes to a stop, that tells me my final velocity is going to be 0. And it tells me the time takes 5 seconds. So that's going to be my time. And the question that's being asked is, what was the acceleration? So I'm going to put a question mark in place of the acceleration. Now, if it doesn't tell us anything to do with position, we can assume the initial position is 0. So we write 0. Now we look and see we don't know anything about final position. So when we look at our equations, the first equation is missing the final position, which is the first dash. So each dash represents the equation. So this is the equation that we're going to use, is the final velocity equation, the first one listed. Now it is important, once you get your equation, that don't plug numbers in right away. What we want to do is rearrange the equation to solve for acceleration first. The reason for this is twofold. The first is if you're taking an AP physics class, when you rearrange the equation to solve for the variable, that's the way it's going to be in most free response questions, is solving for equations symbolically. Second is it's much easier to find an algebraic mistake if you rearrange the equation by using symbols instead of plugging numbers in and multiplying, and you have no idea where the numbers came from that you're trying to figure out. So once we do that, we're going to rearrange our equation. We're going to solve for our acceleration. So we get acceleration is equal to Vx minus Vx naught divided by t. Now we're ready to plug our numbers in. 0 minus 30 meters per second divided by 5 seconds, well, that's going to give us a value of negative 6 meters per second squared. We want to make sure that our answer makes sense. So what do I mean by that? Well, if we look at our speed that we use, 30 meters per second, we assume that to be a velocity in the positive direction. So going to the right on a number line. And when an object slows down, that means that the acceleration should have the opposite sign. So it should be to the left and negative, which is exactly what we have. So let's look at a second example problem. So we're going to use the same problem. We're just going to switch the question up. And how far did the car travel while braking? So we still have our initial velocity of 30 meters per second, the final velocity of 0, time of 5 seconds. We know the initial position is 0. But what we just solved for is that the acceleration is negative 6 meters per second squared. Now we're looking for the final position. How far did the car travel? So 0 to a final position. We look at our kinematic equations, and we have two equations that have a final x in it. And you can see the final x's right here. One of them is going to be much easier to use than the other. And it's not wrong to use either of them, but the third equation is going to involve a little bit more algebra. So we're going to go ahead and pick the second equation, and that will be the one that we will use since it is already solved for what we are looking for. First thing we're going to do is look and see we have x naught is 0, so I can go ahead and cross that out and rewrite my equation. And it's already solved for x, so I can go ahead and plug in my values. X is equal to 30 meters per second times 5 seconds, plus the acceleration times time squared. So let's look at the units. How do the units work out? So when I multiply 30 times 5, the seconds are going to cancel out, leaving me with a unit of meters, which is what I want for position. How do the units work out for the second part? Well, I can see that time is squared, which means the unit is going to be squared. And I can cancel out second squared and second squared, leaving me with a unit of meters. Then I can plug in my calculator. I get 150 plus a negative 75, which gives me a value of 75 meters for the position. So the car travels 75 meters while braking. Let's look at a little bit more challenging problem now. Example problem 3 involves a sprinter running a 100-meter race. As the race starts, they increase their speed by 3.8 meters per second. The sprinter reaches a speed of 11.7 and then finishes the race at that speed. And the question we want to know is, how far did the sprinter run while speeding up? So here we go, listing our variables with the dashes again. Then we're going to go through the problem and we're going to look. And here's what I like to call eye candy. They give you a number here, 100 meters. And a lot of you say, okay, well, that's a position, so let's go ahead and plug that in. But that's not what the question's asking us, is not the entire race. We only want to know, how far did the sprinter run while speeding up? Well, that tells us that he's not going to speed up for the entire race. So this 100-meter is just extra piece of information that we don't need. So let's put a question mark for the final position. Now we have this increasing their speed 3.8 meters per second each second. At first glance, you might say, oh, there's meters per second. That must be a velocity, but you have to keep reading. 3.8 meters per second each second, which tells me that it's 3.8 meters per second or 3.8 meters per second squared, which is our acceleration. Then we have the speed of 11.7 meters per second. That's the speed the sprinter reaches. That's the final velocity. And at first glance, we might see, we don't have enough information to use the kinematic equations, but as the race starts, that means at the beginning, the runner was not moving, so the initial velocity of the sprinter to begin with was 0, and we can assume that he starts at a position of 0 before he starts to run. So now we can see we have everything but time, and we're looking for the final position, so we're going to look at our equations. The third kinematic equation does not have time in it. Now we're going to look at what are the values that we have that are 0. We can go ahead and simplify our equation by plugging 0 in for those and crossing them out. It simplifies our equation. Now we're going to go ahead and solve for what we're looking for, which is the position. So we divide by 2ax, and then we can plug our numbers in. 11.7 squared divided by 2 times 3.8 gives us a position of 18.01 meters. So the sprinter ran 18.01 meters while speeding up and then continued at that speed for the remainder of the race. This is how you use the kinematic equations to solve problems. You got to make sure that you list the variables in that specific order, put your dashes, and the number dash that you're missing, have nothing written next to, tells us the equation that you're going to use. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter at Cavi Coaches.